or on this computer, right? So we have a motorist who's traveling on a curved section of a highway of a radius 2,500 feet at the speed of 60 miles per hour, all right? The motorist then suddenly applies brakes, causing the automobile to slow down at a constant rate. So you have a constant acceleration along the curved path. Knowing that after 8 seconds, the speed has been reduced to 45 miles per hour, determine the acceleration of the automobile immediately after the brakes have been applied, right? So here, the first thing is, again, it's that figuring out what's the best way to do it, right? Here, the best way to do it is looking at the tangential velocity and the tangential acceleration, right? And as soon as you do that, it clicks into place that we should probably use normal and tangential components, right? So the first thing to do would be to define the coordinate system, right? So defining the coordinate system for this car. So you have your principal normal direction, which points towards inside towards radius. And then you've got your tangential direction, ET, like that, right? So first things first, let's, you're working with feet and with miles. So let's just convert everything into feet per second, right? So you have the initial speed of 60 miles per hour. Right, so, oh my God. Yeah. Do you guys remember this? How many feet in a mile? 5,000, 5280. All right, there we go. Times 5280 feet divided by 1 mile. And then let's convert the hours into seconds as well. So you have, let's just write that out again. 60 miles per hour is equal to 60 miles per hour times 5280 feet divided by 1 mile. The mile cancels out, times your hour converted into seconds. You have 1 hour at 3,600 seconds. Right? It's RR. Oops, not that one. That one cancels out, right? So you're left with 88 feet per second, like that, right? And similarly, if actually, could you guys check that for me real quick? So 60 times 5280 divided by 3,600.
It is 88.
All right, thank you. And then similarly, you have this other speed of 45. So let's just convert that. 45 miles per hour is equal to, how much does that come out to be equal to?
$66.
66, thank you. Right, your acceleration is going to be constant, right? Because you said that it constantly reduces the speed. And the quick thing that you can note here is that, oh, Mr. Tillotson, I just saw your question on the chat window. I can tell you when the tutorial sessions are. You should have a Google invite for them. Let me know if you don't, but they are from Wednesdays from 11:30 to 12:30, and then on Monday from 5 to 6. Good stuff. Good stuff. All right. Sorry, I don't know when you posted that. Must have taken a while. All right, so next thing to note is that with the velocity decreasing along the path, that acceleration is going to be the tangential component of the acceleration, right? So we can write that out in an average form. So we can say that the tangential acceleration is that average tangential acceleration, right, which we had given in the problem, and that's equal to delta V over your time, right? So how much your speed changes. You know it's slowing down, so it's going to be a deceleration, right? So you have delta V, which is equal to, final one is 66, and the initial one is 88. So 66 minus 88, and this is in feet per second, divided by, it takes 8 seconds, right? So 8 seconds is going to be like that. This comes out to be equal to how much?
Negative 2.75.
Yep, that's what I got. Negative 2.75 feet per second squared, like that, right? But you've got to notice, and we've learned this when we're looking at these tangential and normal components, that this is not the only component of your acceleration, right? Because immediately after the brakes are applied, how do you spell brake? B-R-A-K-E. Not an English class. Brakes are applied, you know, the tangential speed is 88 feet per second. So you're going to have a normal component as well, right? So you have the normal component of your acceleration, which is just equal to the speed squared divided by the radius of curvature. So we know that that point is 88 feet per second squared divided, well, you know, not like that, 88 feet per second squared, the whole thing squared, divided by the radius, which was 2,500 feet, like that, right? So how much does that come out to be equal to?
$3.098.
So let's say 3.10, right? That amenable to everyone. So you have 3.10 feet per second squared, like that, right? So you can write your acceleration as a vector in your normal and tangential components, right? So in the direction in which we've defined them, it'll be minus 2.75 ET plus 3.10 En. But the thing is that when you're working with tangential and normal components, right, it's well and good for you, for us, when you're solving the problem, but typically you don't report your answer like this, right? The question is asking you for the acceleration right after the brakes have been applied, right? So to find the acceleration, you just take the magnitude of this, right? So for the magnitude, the acceleration is just going to be square root of n squared plus at squared. That's just the square root of 2.75 squared plus 3.10 squared. And how much does that equal?
$1.43.
Cannot be. It has to be more than 2.75 and 3.10.
Oh, I messed up. I put the wrong sign.
No worries.
I got 4.14.
Yep, that's what I got. 4.14 feet per second squared, right? So that's going to be the magnitude. And to complete the problem, you also want to give a sense of direction, right? So what you can do is, you know that you have the circular path like that, right? If you're at that point A at which we're talking about, you know, we know that there's a tangential acceleration, right, which is the negative ET direction, but this is going to be 2.75 feet per second squared like that. And then you have your normal component, which is AN. That guy is equal to 3.10 feet per second squared, right? So you can find out the direction of the overall acceleration, right? So this is the acceleration that we've just found. So this is this guy. Whoops. Right over there, right? So you can find a reference angle, let's say this angle, let's call it theta, right? And you can say, how can you find theta out, guys?
You know, Pythagoras theorem.
What is that? What is Pythagoras' theorem here?
A squared plus, as far as like trying to, I'm sorry, I'm just,
No, you're heading in the right direction.
yeah. Just
Octave.
just using the inverse like sine function or cosine function and using like, the accelerations.
Absolutely. You can do that because you know the magnitude of all of them now. So I guess, you know, there's a multitude, there's many ways to skin a goat. If you hadn't solved for this acceleration before, the easiest way to do it would be to use the tangent, right? Or tan theta. And tan theta, opposite over adjacent. So that is AN over AT. That's equal to 3.10 feet per second squared divided by 2.75 feet per second squared. So what does theta come out to be equal to?
Yeah, 48.4.
48.4 degrees, right? And that gives you the complete solution, right? I am typically not a fan of finding the angles out because if you've already derived the answer in terms of a coordinate system that you've defined, just writing your answer as a vector should be okay, right? So from my point of view, if you express your answer in this form over here, you'll get all of your points. But, you know, I am just one guy, right? For your FE exams and going forward, you know, with stuff that has to deal with dynamics, it's good to know how to do this part of things as well, right? So that's how we do it. All right, good stuff. So any questions with this question?
So at the bottom there, where you have your two accelerations, radial and transcendental, the resulting acceleration is that magnitude that we found at 4.
Correct.
Right.
Or the resulting acceleration is just this vector. This vector completely describes everything.
Okay.
Right? Because from here you can get the magnitude and you can get this angle theta direction as well. That's the whole point of vectors. But, you know, some people like a physical, it's the magnitude is this much and it's at this angle, right? So you do it both ways, right? For me personally, going forward, if you write it as a vector, you guys are okay. All right.
I have a question.
Yes, please.
Which of the formulas you derived did we just use for this problem? Because I don't see none of them two formulas you derived.
Oh, good question. So the formula that we used, let's go. Is this one over here, v squared over rho. And then v dot. But to find v dot, we found the tangent acceleration as an average because we were not given the exact value, but we were told that it slows down along the path by that much.
Okay, thank you.
Right? right? You have your v squared over rho over here, and then you have this average acceleration term in the tangential direction, which is that v dot term, right? But we can't find that one out exactly because the problem doesn't give us enough information for that. So you find out the average one in the tangential direction. Good? Good stuff. All right, so next question is this one. So we have the rotation of an arm about a point O, right? And you have this collar that is sliding along it, right? And you're told that the angle theta changes on as a function of time using this function over here, right? And this theta comes out to be in radians and t is in seconds. And then you're also told that r, this distance r along this collar here changes as a function of time using this function over here where r is in meters, right? So this function of 0.9 times 0.12 t squared is in meters, right? And you're told that after the arm has rotated through 30 degrees, you're asked to find the total velocity of the collar, the total acceleration of the collar, and then the relative acceleration of the collar with respect to the arm over here, right? So next question to you guys is, given this problem statement like this, what coordinate frame do we use? Right? Are we going to use rectangular coordinate system? Are we going to use the tangential normal coordinate system? Or are we going to use the polar 2D coordinate system?
2D.
The polar one, right? Because you're given theta in terms of t, you're given r in terms of t, and you have all of those derivations out for you, right? So the way that we're going to go about it is we'll find out what the time is when the angle is equal to 30 degrees. And then we basically have all of the information we need to essentially solve the problem, right? So the first step is to find the time t for theta equals to 30 degrees, right? So theta is equal to, what's the function? 0.15 t squared, like that, right? But remember that this is in radians, so you'll have to convert 30 degrees into radians. So how many radians in 30 degrees? Excuse me.
0.52.
Does everyone know how to convert between degrees and radians? How do we do it?
Take pi over 180.
Pi over 180. That's absolutely right. So 30 times pi over 180 degrees, right? So radians over here. Degree cancels out. You're left with radians. So this, you guys said 0.524, right? So plug
Yes.
it back in. All right, so 0.524 is equal to 0.15 t squared. Now, you can do this rather easily, but I wanted to show this to you in Mathematica, right? I hope you guys are, whoa, hit the wrong button. Start using Mathematica going forward, right? Solving expressions and things like this is really easy because all you have to do is, hey, solve 0.15 equals to, no, not 0.15, 0.524. Well, too much. Is equal to 0.15 times t squared, right? And you're solving for t. Easy peasy. That's it. You get your answer. Obviously, time can't be negative, so you take the positive time, right? So time is equal to 1.869 seconds. So time t is equal to 1.869 seconds. All right. Then you're told that R, sorry, the scalar R is equal to 0.9 times 0.12 t squared, right? And we know that we're working with polar coordinates, right? So we are going to be looking, whoops, at these formulae over here, right? So we need to find out basically what R dot is and what R double dot is. And then we also need to find out what theta dot is and what theta double dot is. All right. So R is equal to that. So you can figure it out at the time t equals 1.869 seconds. It's just 0.9 minus 0.12 times 1.869 squared, right? What does that come out to be equal to?
$1.32.
1 point. Nope, I don't have that. Can someone check? I might be wrong.
0.48.
0.48? Yeah, I
Yeah.
got 0.48 as well. All right, 0.481 meters, right? R dot is just equal to the differentiation with respect to time. So the 2 comes down, so minus 0.24 t. So at our time, 1.869, what is that equal to?
Negative 0.44.
It is 0.44. And what was the last number? Was it a 9? Let's give it a, I have 9,
It's like
right? So that
8,
becomes,
yeah.
yeah, all right. And then R double dot, right, is just equal to minus 0.24, right? The time goes away. And then the units of this are just meters per second squared. Oh, R dot units are not meters, guys. It's meters per second, like that. All right. And then you have theta, which is 0.15 times t squared, right? So at a time 1.869 seconds, we already know that it's 0.524 radians. Theta dot is going to equal, the 2 comes down, so it just becomes 0.30 t, like that. So 0.30 times 1.869. How much does that give us?
.5607.
All right, so 0.5. .61 radians per second, like that, right? And then theta double dot is just equal to 0.30. That goes away. You get radians per second squared, like that. All right, so here, what we've done is we can define the coordinate system. Just one big thing. Yeah, it is. Anyway, so we'll just do it up top over here. So we've defined our coordinate system such that you have ER and you have E theta, right? So we go on to next page, right? We can write velocity as R dot times ER. There should be no dot there. Whoops. Erase. No dot over there. So R dot times ER, right? So it was R dot times ER plus R theta dot times E theta, like that, right? So R dot, we had found out was how much? R dot was minus 0.449. So minus 0.449 ER plus R times theta dot. So R was 0.481. 0.481 times theta dot, which is 0.561. Like that, right? And this is going to be in meters per second, right? So it becomes minus 0.449 ER. And what is this product equal to? 0.481 times 561?
0.27.
Yeah, 0.27. Thank you. 0.270 E theta meters a second, right? And then from my point of view, problem is done. But again, people expect you to find out the magnitudes and the directions and things like that, right? So you can do that, right? So magnitude of the velocity is just that. Just 0.449 squared plus 0.270 squared, right? And what does this come out to be equal to?
0.524.
0.524. Right, and then, you can also look at your caller, right? You have a V theta direction, you have a VR, like that, right? And remembering that we've defined our frames as ER and E theta, like that, right? So you can find out an angle in reference to the coordinate as well, right? So we draw it out. This is your V. Let's say that this angle is equal to beta, right? So you can find that beta is equal to the tangent inverse of opposite, which is this V theta term, which was this R theta dot, which was 0.270 divided by the magnitude of your VR, which is 0.449, right? And what does this angle come out to be equal to? We've
31
basically
degrees.
sorry, go ahead.
31 degrees.
31 degrees, right? We've accounted for this negative sign over here by saying that it's in the minus ER direction, right over here, right? All right, and similarly, we go back to our acceleration, right? You have this big mess over here, right? So, whoops, the acceleration is equal to R double dot minus R theta dot squared times ER plus R theta double dot plus 2 R dot theta dot times E theta, right? So the acceleration is equal to R double dot, which was minus 0.24. So minus 0.24. Units are all good, meters per second squared, right? And then you have minus R theta squared. So minus R was 0.481. 0.481 times theta dot, which was 0.561 squared, right? So this is ER plus E theta is R times theta double dot. So what was R again? 481. What was theta double dot? It was 0.30. Right, and then you have plus 2 R dot times theta dot. So R dot was minus 0.449. And theta dot was 0.561. Times E theta, right? So what does the first bracket become? The ER term.
.088.
Nope, that is not what I have.
I have negative 0.39.
That is what I have. Negative 0.391. All right, so just in the interest of time, I'm just going to give you guys the answers. Hopefully mine are correct. If you find some issues, let me know. So we have ER, and then this big mess over here. What I got was minus 0.359 E theta, right? And that is in meters per second squared, right? Again, for me, this is a good enough answer, but to just complete it all, right, you've got an AR term, which is in the negative ER direction, and theta, which is also negative, so it'll be like that. So AR is equal to 0.391 just per second squared, and then a theta equal to 0.359. Then you can find out these angles, right? Let's call this one gamma. So the magnitude of the acceleration is just equal to this .391 squared plus 0.359. Guys, we're going to go 2 minutes over. Just bear with me. Which is equal to, what do we get? We get 0.531 meters per second squared, and then gamma turns out to be equal to 42.6 degrees, right? The tangent inverse of things. Now, the last part of the problem asks you to find the relative acceleration of the collar with respect to the arm, right? So if we write it out the way we've been writing it out, is that we have to find relative acceleration with respect to the arm OA. The beauty of using these radial and these polar coordinates here is that the acceleration of the collar with respect to the arm is always going to be in the R direction. So that is just equal to AR in the R in the sorry, it's not equal to AR. It's equal to the rate of change with which this collar is sliding on here, right? So it's basically the rate of change with this collar is sliding on this arm over here, and that rate only changes at a rate of R double dot, right? So the movement of the collar with respect to the arm is only going to be related to how this radius, how this position of the collar changes. So that is just equal to R double dot, right? Because the movement is rectilinear and it's defined by the coordinate R. So this we had found out is just equal to minus 0.240 meters per second squared. All right. Thanks, guys. Do you have any questions?